Hello and welcome to STAT 441, the online course at Virginia Commonwealth University. This lecture is part 3 for chapter 2, which is descriptive statistics. In this chapter, we will discuss some measures of spread for quantitative data. So we have already seen some measures of central tendencies for describing our quantitative variable. Now, let's look at some measures of variation or measures of spread. The description that we had using the measures of central tendency, it is usually incomplete if we don't understand how spread out our data is in addition to where the center of the distribution is. So to understand the variation of our data, we will look at three different types of measures. They are the range, the variance, and the standard deviation. The first measure of spread is the range, and it's very simple to calculate. You basically take the largest observation and from that subtract the smallest observation. So that gives us the range or overall how spread out our data is. Okay. The problem with range is that it just gives the endpoints, and two very different looking distributions could have the same range. So we need to understand more about how spread out the data is. So another measure that we use is called the variance. So let's look at how to calculate the variance. Let's say we have a sample of n measurements, y1 through yn. Then we denote our sample variance with S squared. And as you can see, the formula is a summation of y equals 1 through n. So basically, all the observations, yi minus y bar whole square. So yi is each observation minus the mean. And when you square that difference, that's your the sum of those differences is the numerator. And you divide that by n minus 1. You can solve this to give two different forms of the same formula. This is another useful format. You can use the sum of all yi squared. So you square each observation and then add those minus n times y bar whole squared. So that kind of makes the calculation slightly simpler, but you can use either format. This diagram shows you what this yi minus y bar means. So here we have x instead of y. It's this same idea. So basically, it's the distance between, let's say these dots represent the observations, and the mean of these values is here x bar. Then the distance between these observations and the mean is what we are looking at. This is called the deviation. So some of the values will be below the mean, some will be above the mean. So some deviations will be positive, some will be negative. So if we add them up, we'll get a 0. And that's the reason we square it here, so it doesn't become a 0. So this is how we will calculate the variance of a distribution. Okay. Here's the notation. If we are calculating the population variance, it's denoted by sigma squared. And the same formula, except the y bar has now been replaced by mu, which is the population mean. Okay, so if we have a finite population of n measurements, then sigma squared can be calculated by using this formula. If we have a population which is very large and we don't have all observations, it is usually the value of sigma will be unknown. Okay. Another measure that is related to the variance is the standard deviation. The standard deviation can again be calculated for a sample of n measurements. The standard deviation is simply the square root of the variance. So you can calculate the variance first and just take the square root of the value. You can see it's the same formula except for the square root sign. Same thing for the population standard deviation. Sigma is simply the square root of sigma squared, where sigma squared is the population variance. Okay, now let's look at a very simple example. Calculate these values, the range, the variance, and standard deviation, and then we'll discuss the interpretation of these numbers. So here's a very small data set with only 5 observations. Let's calculate the range first. Range is simple. We take the largest observation, which in this case is 4, and from that subtract the smallest observation, which is 1. So 4 minus 1, 3 is the range of this data set. Let's calculate the variance in the standard deviation. So we can use this format of our formula. We can start by calculating sigma yi squared and sigma yi's. So sigma yi means we add all the observations. That's the sum of all observations. So that is 12. And sigma yi squared will be we square each observation and then find the sum, which is 34 in this case. So using this formula, sigma yi squared is 34, and then sigma yi whole squared. So you take the sum and then square it, divide by n. So that's your numerator. And the denominator is n minus 1, which is 4 in this case. So when you calculate this, it gives you 1.3. You could use this formula also. So you can start by calculating the mean of the observations, and from each observation, subtract the mean, square it, and then add them. So either way, it should give you the same number. The standard deviation will be square root of 1.3, which is 1.14 in this case. Okay, now let's look at the interpretation and think about how we can use these numbers. So first of all, the first thing to keep in mind is that we can have two very different looking data sets with the same range, but very different variations. So here is an example. These two data sets, these are the dot plots. So we have the same range. They are ranging from 4 to 10, both of them. But as you can see, the shapes are very different and the variance is different. So for this one, the variance is 3.3. For the second one, it's 5.9. So we have to be careful while using range as the measure of spread, because it's not very effective in explaining the overall spread of the distribution. The second measure is variance, and we've seen how to calculate it. But the problem with variance is that the units of measurement of variance is the squared of the original data. So let's say if your data is in feet, then feet squared or ppm squared. So it's hard to interpret variance by itself. So therefore, we will typically use standard deviation as a means of describing the spread of the distribution. Standard deviation has the same unit as our original data or the variable y. So let's see how to interpret the spread of the distribution using standard deviation. So there are two rules that are used to understand the standard deviation: the empirical rule and the Chebyshev rule. Let's look at the empirical rule first. Empirical rule is it can be used when the shape of the distribution is approximately symmetric or it's symmetric, and then it works best. So here is how it works. The empirical rule says that approximately 68% of the measurements will be within one standard deviation. So you have mean in the center, and then if you go by one standard deviation on each side, then approximately 68% of the measurements will be within these two values. If you go further by two standard deviations, so mean plus and minus two standard deviations, that will give us 95% of the distribution. And then within three standard deviations, almost all measurements will be within these two values. So let's look at the graph of this. So this is a symmetric distribution. So as you can see here, if mu is the mean, that will be in the middle, and then mu plus sigma and mu minus sigma within one standard deviation approximately 68% of the distribution. Within 2 standard deviation, 95% of the distribution, and within 3 standard deviations, almost all measurements will lie within these two values. Okay, so depending on whether we are using this rule for our sample or for the population, the first set will be y bar plus minus s or mu plus minus sigma. Then for 95%, we have y bar plus minus 2s or mu plus minus 2 sigma. And then for 99%, we have y bar plus minus 3s for the sample versus mu plus minus 3 sigma for the population. Okay, next rule is the Chevyshev's rule. In this applies to any data set regardless of the shape. So it's more conservative. What it says is it is possible that if very few of the measurements will fall within 1 standard deviation, but when you get to 2 standard deviation, then at least 3/4 of the measurements will fall within those two values, and at least 8/9 of the measurements will fall within 3 standard deviations of the mean. Okay, here is a graph showing the Chevyshev's rule. So here you can see the shape of the distribution. It's not a bell shape, but we can see that approximately 75% of the distribution within 2 standard deviations and approximately 90% of the distribution within 3 standard deviations. Okay, let's look at an example to apply the rule. So here the data set is on percent iron content of iron ore specimen, and we would like to describe the distribution of iron content measurements. 390 iron ore specimens that have iron ore content measurements. So we want to estimate how many measurements will fall within 2 standard deviations of the mean. Okay, here is the summary statistics for the data set. We have a mean of 66.7, standard deviation is 0.69. We have, this is the shape of the distribution. It's not heavily skewed, just slightly skewed to the left. Okay, so let's see. So using both the rules, if we use the empirical rule, then the mean plus and minus 1 standard deviation. This gives us the range. Mean plus and minus 2 standard deviations, and mean plus and minus 3 standard deviations. So using the empirical rule, approximately 68% of the measurements will lie between 65.05 and 66.43. Approximately 95% of the measurements will lie between 64.36 and 67.12. Approximately all observations will lie between 63.67 and 67.81. If we use the Chevyshev's rule, then we have these numbers which are more conservative. Now, since the distribution was approximately symmetric, our best estimate for the percentage of iron content measurement that fall within 2 standard deviations of the mean, which is the empirical rule, will be approximately 95% of the measurements. Okay, so these are the measures of variation for quantitative data. Thanks for watching. Please watch the next video for measures of relative standing.